morning, everybody. So today I will talk to you about bioprotection. So first, let's see what's the definition of bioprotection. It's a natural way to inhibit all types of microbial contaminants that can be yeast, mold, or bacteria. And in wine, we rather talk about biocontrol. And this biocontrol not only helps you to prevent flavor defect, but also beyond that, it helps to build up and protect your brand. So again, bioprotection is the art of using natural microbial food cultures to inhibit the unwanted contaminants. So this prevents food spoilage, but also enhances food safety. Fermentation is not something new, and bioprotection is based on fermentation. It's known from a very old time. Some of our food has always been fermented. And what do we do at Christian Hansen? We are really specialized in producing microorganisms, and we use our knowledge to identify the best possible strains, both bacteria and yeast, to be suited for bioprotection. And we would all love that bioprotection enables to remove the sanitation. But unfortunately, that's not possible. That's not, we are in a biological process, so this is not chemistry. And we cannot we cannot be an alternative to a good sanitation. So this will be used on top of the sanitation. So why is it so important to have the process in control by using suitable microorganisms? Because, I mean, having a bad deviation in your process will obviously lead to unclean flavor. And everything, all that you have tried to build up for many years can be compromised in just one moment with a consumer communicating on a bad brand experience via social media. At Christian Hansen, we operate in many applications. We operate in dairy, meat, and wine. And we thought that it could be interesting to give you a sneak peek of what we're doing for dairy and meat in order to give you inspiration. So I will shortly present what we do. And why is it's important for dairy and meat? What is so important to use natural process? And it's because so many consumers are looking at what is on the label. We saw on Euromonitors that 66% of consumers worldwide are just paying attention to the food and drink labels before purchasing a product. We have all seen in supermarkets people looking at the labels, and this is not something that's going to disappear in the next years. So especially artificial preservatives are really in the focus of consumers. So this is why we're lucky that we operate in a natural segment with natural flora, so we can keep the label clean. So first, let's see what we do in dairy. Our protective cultures for dairy have the commercial name of Fresh Q. And in Fresh Q, we want especially to prevent mold and yeast spoilage. And that will enable to extend the shelf life and to keep the product fresh for a longer time. Mold and yeast can come from many sources. Mainly, it comes from the environment. So it's very difficult to get rid of it. And this is why the culture can help. So it can come also from the ingredients. In dairy, they can use, for instance, fruit preparation in yogurt, and that can be the source of contaminants. That can be weather conditioned. If the weather is humid in the autumn, for instance, there is more molds in the air. And the process, there can be pressure on workers, and then the process gets changes. The sanitation can be shrink, so that there are many sources of possible deviations. Here is a slide that we all love, because it shows us, it's a comparison of a sour cream inoculated with various contaminants and molds with and without fresh Q. And the picture is very clear that after 45 days, which is significant, of storage either at 45 degrees or at 54 degrees, we have a very significant difference if we use fresh Q and if we don't use it. For yeast, it's about the same. Yeast are not so visual, so looking at a film, showing a film of yeast is more difficult. That's why we decided to show a graph. Here you see the growth of the yeast, the Brettanomyces Hanseni, which has been inoculated at 50 CFU per gram at the beginning, so a rather low inoculation. And we see that it raises very fast. After 10 days, we have 10 to the 4th CFU per mil of cream, and this raised even to 10 to the 7th, whereas when fresh Q was added to the product from the very beginning, then we had a small growth, but I mean, the yeast remains at a very low level, so that we do not have the defect. So again, it shows that it's not a chemical, so you don't kill everything, but you put pressure and reduce the contaminant at a minimal level. So what can fresh Q do? It can benefit the product in various ways. So first you go natural, because you have to label cultures, but that's the way it is. It is not an artificial preservative. You take control of your process. You stay fresh a longer time, so you can expand the shelf life. And so that's how what it enables to do. Now it brings me to meat. In meat is slightly different. What do we want to achieve? In meat, we might have a problem of contaminants like Listeria or Salmonella. So we also have to reduce them at a minimum level, and that's a health case. So here we use the culture Safe Pro, which are again natural food cultures that we have selected, and that will help to prevent spoilage, extend the shelf life, and also, as I said before, improve the safety of the product. And that's very important for meat. We can also use the culture for salmon or for non-fermented food like salad, for instance. So it makes it, again, easier to deliver a consistent product without any defect. Here is an illustration of the pathogen issues in meat. we can see many reported issues with listeria, both in meat and especially even more in fish. So, of course, this can come from many sources, and it can also come from a high utilization of the material or less sanitation. We also have the issue in meat of creation of biofilms on the equipment that can also generate contamination to the final product. So for meat, we currently use a challenge test that we set up with every single customer. And we use the customer product and we inoculate with listeria. And we see with the protective culture what is the behavior of the product and what is the behavior of the listeria. Do we have any growth, or does it stay at a very low level, or do we even decrease the initial level of listeria? We might also have an impact on the color of the product in meat. So that's something we also check. Here is a curve of listeria growth in bacon stored at room temperature for 29 days. We see that when the concentration was really low at the beginning, log 2, meaning 100 CFU per gram of product, we see that within, let's say, 7 days, it reached a log of 4.5, which means that at this level, it's really a danger for health. And what we see is that by applying the culture BLC77, which is our one of our bioprotective culture, we see that the population of listeria decreases in time. So that's a very good example of the pressure that the culture can bring. So here we have a mapping of the product at different stages, analyzed by sequencing. That's metagenomic analysis. Here we see that before the inoculation with a bioprotective culture, we have several types of species present in the product. We have at least 8 types. And then when we after applying the product, the culture, we only have 2 species, or just a little bit of green, but it's hardly not significant. So we have basically the Pediococci and the Staphylococcus that we have inoculated. That are the 2 species over the BLC77. So we see that they become dominant as soon as we inoculate them in the product. And then that remains the case until the very end of the shelf life of the product, which means that in that case, the product has been protected the right way. So again, for meat, we can go natural because we don't need to declare the culture, the protective culture. We take control of the process, we keep it safe, and we can extend the shelf life in the best way. So that's we can do in meat. And what is the situation in wine? How different is it in wine? Okay, wine is not a dairy product, it's not a meat product. It's very specific, but how can we compare? Here again, for wine, we want to keep the product fresh and clean. We don't want an off flavor, we don't want any deviation, and that we want to achieve. So in that respect, it's very similar to what we want to achieve in dairy. So here in wine, our cultures are called vinifloras. That's our brand name. Some of you might use them already. And that's natural food cultures that originate from the must or from the wine, because we follow OIV regulation. And they are selected to control the fermentation processes. And that's also very important for wine, to preserve the varietal character of the grapes. We don't want to standardize everything around the world. We want to keep the varietal character. What we want to achieve is something more consistent from year to year. Really to enable you to keep your wine signature and not to have good years and bad years. That's the idea. So, where does spoilage come from in wine? It can come from many things. First, we have the grapes, and that's, of course, there are contaminants in the grapes. And that's a high moisture fruit without pasteurization. So from that, it's nearly, it's very easy to have a non-controlled process. We also have weather conditions that can have a strong impact. We can have very bad years and good years. So we have an indigenous flora that we cannot change. And we have a seasonal activity that leads to pressure on workers. We know that they have to do everything in a few weeks. So they run from tank to tank. So they have to do the right things, but sometimes they have lapses. They forget about controlling temperature. They forget about the SO2, or they put double amount of SO2. We can't see anything. So it's another fact that we have to take into account, that there are pressure on the workers, and not everything is under control. So having said that, how does the protective culture work? Again, it's not a chemical. So we have some contaminants from the beginning, that red and purple line. If we don't do anything, the contaminants might raise to a high level. And with the bioprotective culture, we want to keep them at a low level. That's the idea. Not to get the expression of their genes. So we want to go natural. To keep natural, we can use the culture for organic wines or natural wines. We want to take control. That's the most important. And on top of that, if the control, the quality is improved, we hope to improve the bottom line. And we are all paid for that. So first, we want to go natural, and if possible, reducing the SO2. We know that in wine, so far, the SO2 is the only additive which is present in the label, which is mentioned in the label. So this is what the customers are seeing. And so as a consequence, is something that we would like to reduce at a maximum. It's not always possible to remove it completely. It's very difficult, but at least to reduce it. What do consumers think about sulfites? They all know more or less that it's a chemical preservative, that it's toxic, allergenic, that it might give headaches, and that it might damage the flavor of the wine. So sulfites has a very bad name. Also, there is a good reason for the bad name, is that sulfites consumption from wine may exceed the acceptable daily intake. There is a regulation both in US, in Europe, and also, well, I think in all countries now, with a labeling obligation as soon as we are above 10 ppm. And there is also an acceptable daily intake that was set up by the medical organization that is set up at a very low level. It's 56 milligram per day for 80 kilogram man, which means for me, if you see my size, I'm very often above the daily intake. It's very much depending on the wine, especially it's very high in white and rosé, it's very high in sparkling and in sweet wines. So with a couple of glasses, we might be above the maximum daily intake. So this is an issue. Another issue on top of health is that sulfites, of course, is a preservative, so it can help to inhibit the unwanted contaminants, but it also inhibits the flora you want to keep in the wine. It also inhibits your Saccharomyces and the Enococcus. So it's good and bad. And it has also some antioxidant functionality. But this one is difficult to remove, to substitute by a culture. So what we can do with the protective culture is to replace the preservative functionality, and that we want to do. And how we will do it is by taking control of the process. What risk do we face in case of non-controlled processes? First, we have a variable raw material. We cannot standardize the grape juice. We cannot pasteurize. So we face variable raw materials. That's the way it is. We can have, according to the years, high sugars or low sugars. We can have too high malic acid or low malic acid. We can have too high pH, too low pH. And we can have, if the year is bad, we can have a very high contaminants on the grapes. Also, from the agricultural practice, we can have possible oxidation, possible high sulfites, and possible residual pesticides on the grapes. And again, that's the way it is. We cannot do anything about it. As a consequence, if we don't control the process very carefully, we can have a variable microbial activity. We can have difficult or inadequate fermentation. And we can have, of course, a growth of unwanted contaminants. And with an uncontrolled microbial activity, of course, we will have non-mastered metabolites production, meaning that we can have biogenic amines, we can have off flavor or unclean flavor, and we can have volatile acidity. And as a consequence, we can have possible issue on the stock. We can still have Brettanomyces growing in the bottle. And we can have unclean flavor in our wine. If the fermentation is not stopped completely, we can have breaking bottles. We can have too high sulfites compared to the legislation. And we can also have too high alcohol in a final wine if we have very high sugar content at the beginning. So we can have a downgrading value of our stock and a brand damage at the end of the day. A common question is, what is the starting point? What do we have as microorganisms in the grapes? Do we have the Saccharomyces in large amount? Do we have an Eucoccus in the large amount? The result is, unfortunately, no in most of the case. Here we have an example of a sample we took and we analyzed by metagenomic methods. And here you see all the species that were present in the grapes, fungi and bacteria. Just a quick word to explain you the metagenomic methods. It's very interesting because it's less time consuming comparing to traditional plating methods. So it means that you take a sample, you extract all DNA, and then by sequencing, you sort out all the species that you have in one go, and you also quantify the quantity that you have of each species, and you see that in this kind of mapping, you see each strip corresponds to a species, and the size of the strips gives you an idea about the concentration of the population. So meaning that here, in this case, we had a lot of Aspergillus, and we had a lot of Cabatiella in blue. And those species, they are useless in winemaking. They are there, but they are not reported as doing anything good for the wine. And it's about the same for bacteria. Here we see that we have some very exotic species. Here this was a vineyard which was irrigated. So we have some species that was linked to green algae. But they are not of any use in winemaking again. And we had a little bit of Saccharomyces, these little blue strips on the top, but that was only a few percent, so a very limited dosage, very limited CFU. And for bacteria, we didn't find any Eucoccus. So we have the presence of various microorganisms, but of limited interest. So on the opposite, if we control our process, if we inoculate selected microorganisms that we can choose, then we will have a good control on the growth of what we want. For instance, from the very beginning of the process, we can inoculate pre-fermentation yeast, like Lacancea, Pichia, Torulaspora is the one that has been presented by my colleague Antti earlier on this morning. And they will lead to juice and must improvement by reducing the initial concentration of contaminants, because they will put pressure on the contaminants from the beginning. They will also prevent the contaminants from growing. How will they do that? Either by producing antagonistic components, or else by a nutrient struggle, I would say. The most greedy is the one that will take the growth, take the lead. That's more or less the way it works. So we will occupy our must from the beginning. Then we have the Saccharomyces Cerevisiae fermentation, and that's very important because then we will have the rise of ethanol, which itself is an antagonistic component. So this, of course, is very important. It's the heart of the process. And then if we finalize the process by a fermentation, a malolactic fermentation, Then we again drive our process. We stabilize our process. We avoid the growth of undesirable flora, like among the bacteria, we will avoid the growth of the lactobacilli, the pediococcus, the unwanted enococcus or leuconostoc. And also very important, we will reduce the pressure of Brettanomyces. And that's, of course, what we want. We will avoid the off-flavor and the biogenic amines that are linked to contaminants. And also, by this, we can avoid adding SO2 to our process at this stage. We will need SO2 for the bottling, of course, but we can reduce it at a maximum during the winemaking process. Then, as I said, by pre-alcohol fermentation or post-alcoholic fermentation, we get opportunities for the process improvement and for the global safety. By the pre-fermentation, we will have an early colonization of the must or the wine. We might have antioxidation functionality. We might have lactic acid production, which is an antagonistic component. And that's fortunate. We will not inhibit Cerevisiae. It will be the opposite. We prepare the medium for a good alcohol fermentation. So there is a good synergic effect on Saccharomyces and also on Enococcus. And we have the inhibition of undesired bacteria and yeast. On top of it, that's not part of bioprotection, but that's, I would say, the icing on the cake. We will have production of aroma precursor and possible improvement of mouthfeeling, as my colleague explained to you earlier on. Then with the malolactic fermentation, we will have also a colonization of the medium, and we will hopefully have the inhibition of Brettanomyces and lactic acid bacteria. And as a consequence, if we master the process, we can protect the stock value and the brand value by flawless wines, reliable process that you can document, vintage to vintage consistency, possible health impact if we have no biogenic amines, if we have less SO2, and that's a natural solution. So to finish with, I will give you 2 examples of yeast and 2 examples of bacteria. So first, as my colleague showed you earlier on, we will talk about Concerto. That's our Lacancia thermotolerance. This yeast will have a strong colonization of the must from the very beginning. It grows very fast. It produces lactic acid. As I said, lactic acid is an antagonistic compound. And this will result in a higher TA and lower pH. So that helps for bioprotection. And as a consequence, there will be reduced growth of wild bacteria and fungi. And there is a specific inhibitions towards acetic bacteria like Acetobacter or Gluconobacter. And we have a good synergy, again, with the Saccharomyces Cerevisiae, with a fast implementation of the Saccharomyces. Here, this is an illustration of the effect of Concerto by the metagenomic analysis. Here we have taken various samples at various times, and we have analyzed the composition in fungi. And here again, you see that at day 0, you have many things in your grape juice, but hardly no Saccharomyces, just a small yellow strip. Then at D1, when you inoculate Concerto, you see its presence in purple. You see that it occupies about 70% of the total flora, so it's very significant. You see that it stays until the end. And what is also interesting is that you can visualize the growth of the Saccharomyces. Here in D2, the Saccharomyces was inoculated, and you see the yellow strip. And you can see that it grows at D3, and even more until the end of alcoholic fermentation, and then it stays at the end, until the end. And what about the rest of the flora? You see that it's very much reduced. Some of the strips disappeared completely, and some they are really at a lower level. And no one dominates. So this is the illustration of the bioprotection phenomenon. And here you see on top of that, you have, as I said before, the lactic acid production. Here we see in this example a little more compared to what my colleague has shown you this morning. We could see that we could reach 1.6 gram per liter of lactic acid, which is very significant. And we can also see an effect on the pH compared to the control with Saccharomyces. So again, this is an illustration of what it does. And then my other example this morning is about Frutzen, the Pichia, that my colleague has presented to you. One of the advantages is that it prevents from oxidation, the must. We also have a production of lactic acid. We have an inhibition of the growth of bacteria at an early stage. Here, I want to stress the fact that it has an early stage, because then the population of Frutzen will reduce when the alcoholic will raise. So it only protects at the beginning. But sometimes protecting at the beginning is very important, because especially when you have a long shipment of your grape from one place to another place, it can stay under the sun sometimes for hours. And then you don't know what's happening in the grape juice. So it's very important to protect from the beginning. So, and again, here we have a boosting effect on Saccharomyces, so a good synergy. And as it was shown this morning, an additional interest is the flavor molecules that Pichia can provide. So you get thiols and esters on top of the bioprotective functionality. Here is an illustration of the action towards oxygen, the oxygen scavenging. Here you see two examples. One is on Sauvignon at cold setting. You see in blue that a control, and in yellow and pink is with Frutzen. In green it's with Prelude, but it's not as obvious with Prelude. With Frutzen, we really have an effect on dissolved oxygen at every stage of the cold stating. Here is another example from New Zealand, where they have shown in green, when we use Pichia, that we can reduce the medium much faster compared to Saccharomyces. Here is another illustration of what Frutzen can do, this time on bacteria. That's the mapping of the bacteria over time. And what you see is that in that case, Frutzen has been inoculated in skin contact, so from the very beginning at the truck level. And then we see from D0 to day 2 that we have a similarity of all the sequences. that indicates that there is no real bacterial growth during this period, meaning that none of the strain that is present at the beginning is taking over. They stay at a rather low level. If we also evaluate the CFU per milliliters, we could see that we had a reduction of the global bacteria flora. And then the situation gets different when we inoculate with Enococcus at day 13. We see that this time Enococcus will take over. So we have no effect on the later stage on Enococcus. So to finish with, here I will show you two examples of the bioprotection with Enococcus uni. I cannot show, we cannot show what all bacteria is doing, so we take the example of the CH16, which is one of our best sellers that can grow even at high alcohol, in a high alcohol wine. Here we have a strong colonization. This strain is able to grow very fast. We have no production of biogenic amines. This is something when we select a strain, either bacteria or yeast, we select that there is no production of biogenic amines. So we need to be sure of that from the very beginning. And we have a fast consumption of malic acid, which will enable to have a protection towards Brettanomyces and protection towards unwanted lactic acid bacteria. I mean lactobacilli, Pediococci, Leuconostoc, or wild Enococcus. Here is again some experiments we've done at various times on must and wine. Here is the must on the first days, and then at day 13, the must, well, the wine has been inoculated with CH16, and we see that it's very present from this stage, but even we see that it grows and stays until the very end of the wine. Here we see in the bottle that we have about 98% of the population, of the bacterial population is represented by Enococcus. So it's very dominant until the very end. And here is an illustration of the histamine you can have with spontaneous flora. In green, we see that we reach nearly 3 ppm of histamines, and this is much above the threshold for sensitive people. And in some countries, there is a maximum histamine allowed in the wine. It's in Germany. Maybe it will come in other countries. But we see that with CH16, we remain at a very low level of histamine. And to finish with another example of Enococcus, here this time it's Cine. Cine is a very specific strain. It's a citrate negative strain, meaning that it has no citrate permease gene, so we cannot uptake the citrate. And if you metabolize, the Enococcus metabolize citrate, it generates diacetyl. And diacetyl gives a buttery flavor, and it's not always wanted in wine. In some wine, it's well accepted. In other, it's just unwanted. For instance, in Sauvignon Blanc, you want to keep the high fruity flavor, and you don't want a buttery, milky flavor or caramel. So in that case, this is the reason why in many white wine, there is no malolactic fermentation, because winemaker wants to avoid this diacetyl production. But if you have a diacetyl negative strain, then you can achieve the malolactic fermentation without any trouble. So you can stabilize your wine without the drawback of the diacetyl. So here again with this strain we have a strong colloidization, no production of biogenic amine. We have a fast consumption of malic acid. So we have a stabilization and a protection, but we have no diacetyl production. And this is illustrated here. We see the kinetics of the malolactic fermentation. The malic acid is consumed at the same speed as another, I would say, classical strain, the Unos strain. But if we consider the citric acid, we see that it stays at the same level. It's not consumed at all. So, and that's illustrated here also. We don't have any diacetyl with Cine. And the consequence for the global flavor of the wine is that if we compare, for instance, the green bars with CH35 together with the red bars that we have with Cine, we can see that with Cine we have some more fruity flavor like mango, pineapple, or peppery flavor, but we have no roasted, buttery, or milky, or even honey flavor. So this is very specific, and these strains enable to inoculate the white wine that we would normally not inoculate, so we can protect it without the risk of diacetyl. So here I will not comment. This one is a recap of what every culture can do regarding bioprotection, which target it has. So, of course, improving the quality of the wine will hopefully enable to increase the profitability per hectoliters or per gallon, because even with a poor grape picking, poor grape harvest, we can increase the quality. We can also increase the vintage-to-vintage reliability, so you can really build your brand on more consistency. So hopefully you can sell to higher price. So that's a recap on what you can do both with pre-fermentation yeast and Enococcus honey. So I would like to thank you for your attention this morning. I don't know if we have time for questions or the...
So you said that the biocontrolled, bioprotected reduces the potential alcohol.
Yeah, the concerto. You want to know how? It's because it turns a certain amount of sugars into lactic acid. So you have less sugar converted to ethanol. So that's the way it reduces the total amount of ethanol.